Hi everyone, I'm Xihong Wang from Shanghai Jiao University, China. Today I want to introduce a very hot machine learning model called uh, graph neural network and talk about how to deploy it online via a graph database system. And this work is done by Shanghai Jiao University and Ant Group together. I hope you can join this talk. Graph structured data have a lot of applied sense, such as we can model the relationship in the social networks, or we can forecast traffic flow on the road network. And the other applications include protein and drugs relationships, and high energy criticals in LHC machine, or the microstructure of molecules. And so graph data provide a more explicit and expressive way to describe the relationship in the nature or in the human society. Then let's talk about what is a graph. Graph is a kind of data structure that includes many nodes V and their relationships H, E between them. Note that if graph whose nodes have corresponding node features, we call it a node attributed graph. Similarly, we can also assign features to edges. The edge features can represent edge direction, edge weight, different edge types, or the time step when the edge occur, or something else. Although the machine learning has a lot of successful application, but there are some existing problems on how to use machine learning into a graph field. Graph neural networks are proposed to fix these problems. And generally, there are a lot of hot research topic and applications. As we can see in this picture, GN has regularly among the top, and the fastest group, the fastest growing keywords for the top machine learning conference, ICLR, International Conference on Linear Representations. So, GN can be seen as currently experiencing their moment of explosion. So, what do GN do? GNs do. The task of GN is so simple that we put a graph into GNs, and the most common output of GNs is that the model outputs the embedding of each node or the representation of each node. For instance, if we got node embedding of a given node, we can predict the node type of it is a right node or a blue node. Yeah. If we have two node embeddings, we can predict whether there should be a link between them. If we have a lot of node embeddings, we can judge whether those nodes belong to the same community in the graph. So the node embeddings is so important, but the question is how do we obtain the node embeddings? Here is the simplest way of GNN model that. If we want to compute the embedding of the node V1, we can aggregate information from its neighborhood nodes. For example, V3 and V5, V8. We call these three nodes one hoop neighbors or distance one neighbors. And by using this simple aggregation function, here we use a sum function and a simple neural network F. The reputation and the node features of neighborhood can be collected and transform it to update the node feature V1. And like the traditional neural network, we start CNN layer by layer, which can expand the principal field of the model, and eventually acquire enough information from the one hope neighbors and the two hope neighbors or the entire graph. So let's talk about stacking multi-layer CNN, how it works. We can explain this using this figure. And in the beginning, the nodes only know about themselves. And in the next step, this figure is a case of one layer. And in the next step, in the case of two layers, the nodes not only know themselves, but they will know they will obtain knowledge from their distance one neighbors or one hoop neighbors. And the next step, the circle will be expanded to the neighbors of neighbors, which we call two hoop neighbors. So by doing this step by step, a node can learn the knowledge from the whole graph, from the entire graph. Although genes provide a promising way to capture graph patterns, however, those models are designed to deal with static graph. But the graph data in the real world are essentially dynamic. Nodes and edge on graph can appear or disappear over time, and even node attributes also may be changed. For example, in the social media networks, users often transfer their interests to other entities in a short time due to some hotspot event. Or in the economic networks, the people usually spend the money or transfer their money to a new company. A new company transfer their money to another new company. Is a dynamic graph. So in this dynamic graph, if a node is changed or involved in a new interaction, then the embeddings of their nodes should be updated. But yeah, but the thing is that if the interactions happen so fast, then the database might be overloaded. Let's see in this picture. If the node v3 has already changed, and in this moment I want to compute the embedding of v1. So we need to query v3, query v5, query v8, and then we query v2, v7, and v4. We query them all, and we aggregate information and computing some neural networks, and we finally get the embedding of v1. But this progress is a cost of time and a cost of computing resource. So maybe it might be a stress of graph database. So to address this problem, we proposed our model to speed up the inference speed and reduce the complexity of the entire computing link. And here we propose our model, our framework, asynchronous GNN. The traditional GNN we call synchronous GNN. If you want to check many transaction is freed or not, we need to random query their one hoop neighbors in this line, and we use their one hoop neighbors to find two hoop neighbors in this line. It will spend a huge of time to obtain the final embedding outputs of GNNs. To give a vivid example, if a free detection system cannot ban the fried transaction immediately, so the fraudster may escape from the platform and withdrawing the bad money before the platform's responding, and causing the immeasurable economic and reputation losses to the financial platforms such as Alipay and their users. So in our proposed asynchronous GNN, we don't need to query neighbors before the final inference, the final decisions. We use the last update embedding to predict a conclusion that this transaction is fried or not fried, and then we propagate the inference of this transaction or this interaction to their neighbors. We let their neighbors know what happens in this transaction. So it's like a water wave. If a water drop into a pool, the wave will span to the other place. And so let's talk about the detailed construction of our models. Asynchronous propagation attention network APAN. APAN has two links. The first link is synchronous inference link. In this link, we do need a graph, any graph things, any graph stuff, and an asynchronous propagation link. So in the asynchronous link, once the interaction is completed in this line, the detailed information of this interaction will be delivered as a mail to the mailbox of its key hop neighbors through the graph. And in the synchronous link, when the interaction occurs, APN does not need to query the neighborhoods in the graph database, but only resolve the mailbox and then generates real-time embeddings instead. So by the way, you may have the question that why we use mailboxes to restore the propagated information? Because the reason is that the mails with timestamps in these mailboxes are used to deal with the problems of disorder problems in the distributed graph database or graph system. And the propagation module in APN is a core module, and at the same time is the propagation module is actually a highly customized computing framework. It can be divided into 5 parts. The first part is mail generation. Once a node has involved in an interaction, APN aims at generating a mail to record what happens in that interaction. A simple form of mail is just a sum of this node embedding on the each features. And we use the simplest form to establish our model. And the second one is how to choose the neighbors. We use a temporal neighborhood sampling by the key hop most recent neighbors. Yes, why we update this neighbor sampling strategy? Because we our APN aim at modeling the change trend, the rapid change trend, and updating the model embedding. So the most recent neighbors have a lot of um, time information or temporal information, and easier to restore the time information from the most recent neighbors. And so let's talk about the third one. Third one is a mail passing function. After determining the propagation boundary in this part, we need a function that used to define a reasonable mapping mode of mails, which means the mails should how the mail doing message passing through the graphs. In our work, we just use identity function, which means that the mail is being propagated with nothing changed. And the third one is mail reducing. And in practice, a node rarely receives multiple mails during mail propagation. And some active, super active or high degree nodes rarely receive more than one mails than the receive more mails than the low degree nodes. To avoid this imbalance, we use a reduction function of mean operation to transform multiple mails into one mail. And the last one is mailbox updating. Once a node receives the mail, its mailbox should be updated to summarize the historical state of the node's neighbors. So to be more accurate, we adopt first in, first out query data to update the mailbox. Through the query data structure, the mailbox will return the latest information and discard old mails. So let's talk about the performance. APN has been widely tested in 3 real-world temporal graph data sets, including 2 public data sets and an industrial online payment data set collected from Alipay. Well, as we can see, the result of our APN is pretty good. And here is the speed. Compared with other advanced graph deep learning models, APAN achieves significant inference speed improvements with competitive performance. It is 10 times improvement. But note that in a real system, the speed increase of APN is much greater than 10 times, because in our implementation, the whole graph is stored in the single PC memory, whereas it should be stored in a distributed graph database in the real platform. So the reading efficiency of a large-scale graph database will be the bottleneck of the entire system. Well, it is not the bottleneck when using the single machine memory. Okay, generally designed by algorithm researcher and database system experts, APN is the first GNN algorithm that could achieve millisecond level and super large scale inference within the online distributed graph database. We believe that machine learning scientists and computer system experts should work together and make some chemical reactions to come up some cool ideas like our APN. Thanks.